My name is Affan Abbasi, and I'm a PhD student at University of Arkansas in the Electrical Engineering Department. The title of my talk is Wireless Sensor Node Platform for In-Plant Stress Monitoring. This is the outline of my presentation. I'll briefly talk about the objective of this work, and within that, I will talk about the selection of corn plant. Afterwards, I will explain the system architecture and its working principles. Then I will talk about the circuits that we have designed in a 130 nanometer silicon germanium process. Lastly, I will summarize my talk and share the future work for this platform. Afterwards, I'd be happy to answer questions. Smart agriculture or smart farming is relatively a new field, but lots of work has been done in this area that is mainly focused to increase the yield of the crops. There are many systems that uses drone technology to monitor the crop field for discoloration of the crop, and there are systems that monitor soil nutrition levels and other soil parameters. However, systems for in-plant health monitoring are limited. Our objective is to develop a wireless sensor node for in-plant sensing that should not impact the plant growth, and the sensed data can be extracted wirelessly upon user request. Then later on, that acquired data can be used to allocate resources efficiently and develop predictive models by using machine learning algorithms. So why did we choose corn plant? There are a couple of reasons behind that. First one is that the increase of corn acreage in the last 15 years in Arkansas is prominent. It is largely because of the profit potential compared to other crops. Secondly, the stalk of the corn plant is thick enough to insert the sensor in it. In addition to that, we have the test bed for corn plants in soil, water, and agriculture department, where we can control the environment for the plant. The metrics that we want to target are battery lifetime, data transmission, size of the sensing platform, and the impact to crop growth after sensor insertion. We tested metallic tubes first in the corn stalk, and due to the moisture in the plant and in the environment, they got rusty, which potentially be detrimental for the plant growth. So we choose fiberglass tubes and made a chisel type cut on one end to be able to insert it inside the plant. We built a tube by using 3D printing, and it is shown in bottom right picture. Also, we used a commercial temperature sensor soldered on a flexible PCB and inserted in fiberglass tube. This is the system architecture. An FPGA is used to control the system operations, which would eventually be realized on a chip in future. The circuit blocks shown inside the yellow region are designed on chip in a silicon germanium 130 nanometer process. Main power source for the system is the micro battery. It is giving power to the design chip, the sensor, and the WakeUp receiver, along with other blocks on the PCB. Micro battery is directly connected with the TR switch and the WakeUp receiver to keep the system always in listening mode when it is initialized. The WakeUp receiver triggers the system operation by detecting the user request, which is a 433 MHz signal. After the reception of trigger signal, the FPGA initialized the LDOs and bandgap reference circuit, and also activates the control logic that sets the TR switch into transmit mode to connect the output of the power amplifier to the antenna. Then FPGA sends a data read request to the sensor by using I2C protocol and receive the data. Then data bits are shifted out by controlling on-off keying block that is connected on the VDD of the power amplifier. We also designed LNA and peak detector, but we are not using it in this prototype. The DC power for the design prototype is provided by the 1 centimeter square sized micro battery that has a total energy capacity of 278.6 joules. Our calculation shows that the battery capacity is sufficient for a month-long operation for this prototype. The WakeUp receiver and TL switch consumes 1 microwatt of power, and the total energy consumption for one transmission event is 2.5 microjoules. This means if we transmit data every hour for a month, the battery should last over a month. However, the chemistry of the battery increases its output resistance with the surge in current. Therefore, in order to keep the stable voltages for circuits, two LDOs are designed. The schematic is shown on the top right. One LDO has 1.2 volt output for RF circuits, and other one has 2 volt output, and it is for the sensor. The graph shown on the bottom right is the quiescent current versus supply voltage results for LDOs. The quiescent current increases with the increase in input voltage, which is expected. The output voltage for LDO is measured as line regulation and load regulation. The line regulation for 1.2 volt LDO is measured to be 0.56% per volt, and load regulation is 0.5% per milliamp. The line regulation for 2 volt LDO is measured to be 1.75% per volt, and load regulation is 0.265% per milliampere. To transmit the sensed data wirelessly, Class AB type power amplifier is designed. Its schematic is shown in the top right. Linear power amplifiers has good linearity, but they are power hungry circuits. For this design, we limit the current to 3 milliamp with the trade-off of having a lower gain that is measured to be 3.5 dB. Our operating frequency to transmit data is 433 MHz. So the passive size required for the matching network are large, and that is why we couldn't do the on-chip matching for the power amplifier. Instead, we did it off-chip on the PCB. Linearity for the power amplifier is one of the features of merit, and it is represented by the 1 dB compression point. We designed it to amplify lower power levels. The measured data that is shown bottom right graph shows that it is linear between -45 dBm to -1.75 dBm, which is close enough to our design specs. We couldn't measure it below -45 dBm because of the limitation of the equipment. For the WakeUp receiver, we designed a semi-active circuit. It consists of a voltage multiplier that is made up of passive components and a low power comparator. The benefit of using this approach is lower latency rate and reduced power consumption. In addition to that, we choose adaptive reference voltage on the comparator by using an RC network. This helped in increasing the dynamic range, meaning the moment we get some RF power, the comparator will trigger the FPGA logic. The sensitivity we measured is around -40 dBm, and generally this depends on the impedance matching network. Showing on the bottom right is the full board with the designed chip. The size of the chip is 2 mm by 2 mm. In summary, we met 3 of the metrics. No impact noticed on the growth of the corn plant, 1 month lifetime criteria met, and wireless transmission on user request. Our future steps are to reduce the form factor for the system to be able to fit it inside the 10 centimeter cube area. We can also do some heterogeneous integration of the system inside the cube and test this platform with other types of sensors. We want to deploy the system across a large corn field to collect the data from different zones of the field and then feed that data into machine learning algorithms and develop a predictive model for stress monitoring. Thank you for listening. Now I'm open to take any questions from the audience.